Okay, here we are, folks. This is the first of several videos on the ellipse. I'm basically working right off of the conic sections notes, so if you have that, you can download that from Blackboard. That's exactly what I'm going through. I'm just going to walk through this. I'm not going to do any numeric examples until the next video on ellipses. All right, so just to give you an overview, on Blackboard, what I'm doing now is from the conic sections notes PDF, and there is also a PDF on classwork exercises on Ellipse. Page 1 is a matching column, which is basically fairly easy, and page 2 is I give you a diagram of an ellipse, and the idea is to write the equation of the ellipse and find the major axes, the minor axes, the center, the foci, length of the latus rectum, things of that type. So it's going to be excellent exercise as classwork practice. I'm going to save the whiteboard video to do some complicated problems, which will be very much like the ellipse take home, which is due, I think I had it Monday. You have to check the date. Check the date. It's on Blackboard. Okay, so this is the first video on ellipses. It's theory. The future videos will be applications and working out problems. So here we go. Definition of an ellipse. Locus again means location, or it's a set of points. So an ellipse is the locus of the set of points x, y such that the sum of the distances from two fixed points, and they're called the foci, f1 and f2, is a constant. Okay, so in other words, from f1 to point P on the ellipse plus the distance from P to f2, that is a constant. Okay, now the ellipse can come in several orientations. It can be mostly horizontal. In this case, the x-axis, the horizontal is the major axis. It can be vertical, in which case the major axis would be the y, or it can be tilted, and we'll deal with that later on. But in this case, from negative a0 to a0 is called the major axis, because it's longer than from 0b to 0 negative b, which is called the minor axis. Where they intersect is called the center. So the center here, as you can see, is 0, 0. And what we're going to do is we're going to be translating these later on, but right now we're going to assume it's centered at the origin, and the one that we'll be looking at is the horizontal major axis derivation. And then we'll just talk about the differences if the vertical axis is the major axis. Okay? All right, so moving along, we got a center at 0, 0. The foci, F1 and F2, are located at negative C0 and positive C0. And the vertices on the major axis are vertex 1 here is a comma 0, and its match vertex 2, I guess depends how you label them, would be negative a comma 0. So the length of the major axis would be 2a, and the length of the minor axis here would be 2b. Okay, so going back to the locus definition, the sum of f1p plus f2p, those lengths, is a constant, and it turns out the constant is 2a. Now, how would you know that? Well, let's just look at the picture. Imagine that point P is right here. Okay, then one of the blue lengths would go from f1 to this vertex at a0, and the other would go from f2 to a0. And you can see that together, those two lengths, because of symmetry, add up to 2a. Okay, so the idea is, that using this diagram and visualizing P to be at either end, it can be seen that PF1 plus PF2 is 2a. And now what we're going to do is we're going to use the distance formula to convert this idea into an equation or a standard form of an ellipse centered at the origin with the horizontal axis being the major axis. And then later on we're going to realize that the lattice rectum length is 2b squared over a. I'll demonstrate this. Eccentricity by definition is c over a. Okay? All right, so here we go. In an ellipse, A is constant, and just looking at this diagram, A is the length from the center, or 0, 0, all the way over to here, and C is the length from 0, 0 to here. So you can see that in an ellipse, A is greater than C. So just keep that in mind as we go along. Okay, so here we go. Using the distance formula, PF1 is y minus 0 quantity squared, x minus a negative c, which is x plus c quantity squared under radical because it's distance, and PF2 would be y minus 0 quantity squared, x minus c quantity squared under radical, and their sum would be equal to 2a. Okay, so that's where this comes from. And what we're going to do is we're going to end up squaring this to get rid of the radicals. Okay, and I know some of you have some issues with this, but it's going to work out. We'll have to square twice, but we'll see. Okay, so what we're going to do is we're going to take this term and move it over to that side, because I don't want to have to square a binomial where each part is a radical. Okay, so we're going to move this over. Okay, and now we're going to square both sides. So let's take a look at that. I'll go through it quickly. This side squared is simply x plus c quantity squared plus y squared. And this side squared, this is a binomial squared. So it's this guy squared, which is 4a squared. This guy squared, which is what's under the radical. And then 2 times this. So it's minus 4a times what's under the radical. So we went from 2 radicals to 1. No, that's called progress. So what we do now is we square these binomials because a lot of terms are going to cancel out. So over here you get x squared plus 2cx plus c squared, and over here x squared minus 2cx plus c squared. You move all those guys over and you can see a lot of things cancel. You got x squared minus x squared, c squared minus c squared. That's after we move all those guys over. Okay? And so we're left with, on the left side, 4cx minus 4a squared. And on the right side, we want to isolate the radical now, so we don't have to do any more nasty squaring. You get this. Okay, so here's what you've got. Okay, you got 4cx minus 4a squared equals a negative 4a times nasty radical. And 4 is part of everything, so we're going to divide everything by 4. Okay, and then moving along, I don't think we need that. Okay, so moving along, we get this. Okay, and we're going to square again. So it's the second time we're squaring. So you just go through the process. You get a, negative a quantity squared is a squared, and this part squared, of course, is what's under the radical. Notice I've worked out x minus c quantity squared to be this. And again, you get a lot of canceling. So when the smoke clears, we're going to actually get a fairly simple standard form. Okay, so let's see what we get. Over here, I'm multiplying it out. A squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared. Now, these guys are like terms on both sides. They're identical. Boom, they go bye-bye. And we're going to get all the non-x terms together. So we're going to move some stuff around. We end up with this line here. Okay, and we're then going to turn things around because we want the x's and y's on the left, and we're going to factor out the x squared here. And this is what we get. We get a quantity a squared minus c squared times x squared plus, and you can read this for yourselves. Okay, so now we're going to divide each term by a squared times quantity a squared minus c squared for the simple reason. So if you know the end result, this is obvious. We want a 1 here. So whatever is on the outside, in other words, doesn't have any x's or y's, we want that to be a 1. So how do you get it to be a 1? Divide everything, each of these 1, 2, 3 terms by this expression, and you end up with x squared over a squared plus y squared over a squared minus c squared. At this point, we want to simplify things, so we're going to let a squared minus c squared be a b squared, and this becomes our standard form. Now, you might going to say, well, this looks a little bit like the Pythagorean theorem. You're right, it's not, but it's not. The reason why it's not is because a squared, or a, is greater than c, right? We talked about that here. Length of a is greater than c. So what you're doing here is you're thinking like the Pythagorean theorem, but it's going to be that the a squared is going to be sitting by itself. Okay, so the alternate form, well, let's just talk about that again. A squared minus c squared is b squared. So this is what you need to know for an ellipse. Okay, so this is going to be our standard form. Okay, notice that the a goes with the x. So whatever is the major axis, that length is 2a. So in this case, the major axis is the same direction as the x-axis, so therefore the a term goes under the x term. Okay, so important to understand, this is standard form of an ellipse centered at 0, 0, where the x-axis is the major axis. Now, what we can also do is we can do a translation, meaning instead of the center being at 0, 0, it can be at HK. We've seen that kind of thing before with circles and with parabolas, so this should not be a surprise. So here's the idea. If the center is at HK, instead of having just an x squared, we have x minus h. Instead of having just a k, or y squared, we have y minus k. And then it gets squared, of course. This would be if the major axis is vertical, and this is the form if the major axis is horizontal. Now, here's what you got to watch out for. Look at where the a squared is here compared to where the a squared is here. The a squared goes with the variable along which is the major axis. So in this case, the major axis is horizontal, therefore the a goes with the x part. Here, the major axis is vertical, so the a squared goes with the y part. So that's the thing you have to watch out for. All right, if you can get that by looking at the diagrams, and as I said, there are some classwork exercises where you do a matching column, you have the equation and the graph, and then the second page of that is where you get the graph, got to write the equation. If you can do that kind of thing, you're going to need to recognize these two patterns and distinguish between them, because that'll determine which is the A and which is the B. Okay, and in each case, a squared equals b squared plus c squared, a little out of focus, so it's probably better in the print. Okay, so that's what you need to know. This is what you need to know. Okay, so if you understand this, live with it, it will work out. Now, a couple little items here. Notice, a couple of notes here. In an ellipse, a is constant, right? Because 2a is the length of the major axis, regardless whether it's vertical or horizontal, the 2a goes with length of the major axis. And a is greater than c, because as we saw, a is further out. See, let's go back here again and look at that. This is length c, associated with the focus, and this is length a, associated with the major axis. So a is greater than c, okay? And in an ellipse, a squared equals b squared plus c squared. So it's almost like the Pythagorean theorem, but it's a little bit tricky because The greatest length is the a, and that's why the a squared stands alone. Okay, second and final little thing is, why does the length of the lattice rectum of an ellipse equal 2b squared over a? Now you can memorize it, but I would rather not memorize things. So let's go over this nice and slow. I made an additional diagram here. And this diagram appears in the new version, I updated it, of the conic section notes, which is on Blackboard. This one, chapter 11. So you definitely want to print this out. It's all there for you. Lattice rectum, let's just do a review, is the line segment which passes through a focus. I'm just drawing one here. There would be another one here. I'm just drawing one. Is a line segment which passes through a focus and is perpendicular to the major axis. So in this case, it's wider than it is high, so this is a horizontal major axis. So the lattice rectum is going to go through a focus perpendicular to the major axis, and it's dotted in red. So what we want to show is that length is 2b squared over a. All right, and that's going to help us graph these things, because once we know what the length is, then we're going to start to focus and go halfway up that amount and halfway down and get an idea of how narrow or how wide this ellipse is. So that's going to help us with our graphs. Okay, so just to review, focus is at c comma 0, and since this line is vertical, it has an x value at this endpoint at c, and a y and an x value at this endpoint at c. Y up here is positive, y down there is negative, so you can see that this length, since it's vertical, is simply y minus negative y, or 2y. So the length of the lattice rectum in this case is 2y. What we're going to do now is go to our equation and figure out what 2y is. All right, so here we go. Here's the basic pattern for major axis is horizontal type centered at the origin. Okay, and what we're looking for is, we want to find y, because we just said length of the lattice rectum is 2y. So what we're going to do is solve this for y. And what we're also going to notice is that the x value is a c. Okay, so we're going to substitute in c for x. Okay, and then we're going to solve for y. So these are fractions. We don't like fractions, so the LCD is a squared x squared. Multiply each of these 1, 2, 3 terms by a squared x squared, and you get b squared c squared. Oh, yeah, a squared b squared multiplying by. So you get b squared c squared plus a squared y squared equals a squared b squared. And now again, let's not lose focus. We want to solve for y. So I'm going to take this term, move it over, it becomes negative, and then divide by a squared. So this is what we get. Okay, you got a b squared in each of these. I'm factoring out the b squared, and look at this. You got a squared minus c squared, but remember, in an ellipse, a squared minus c squared is b squared. Okay, so therefore, this is b squared. So you get b squared times b squared is b to the 4th over a squared, but that's y squared. So we take square root, both sides, and normally we put a plus or minus here, but we're working in a positive half, so y is b squared over a. Therefore 2y, which is what we were looking for, right? Length of the lattice rectum is 2b squared over a. And what we're going to be doing, if you do the classwork exercises, is we're going to be practicing finding the length of the lattice rectum. And once this guy is in standard form, you can just look at the a and b and tell what the length of the lattice rectum has to be. Okay, so that ends the theory part of the ellipse, and what we're going to do next is we're going to have 2 short videos where we begin with an equation in non-standard form, which turns out to be an ellipse. We're going to put it in standard form and find all the missing parts. We're going to find the A, B, C, according to the vertex, in major axes, lattice rectum, foci, everything. We'll do it step by step, and then you'll be able to do it as well on that problem set take home for ellipses. Okay, so that ends the demonstration on the theory part. Now we're going to go to the whiteboard in a future video. Hope I can get my act together with cleaning that up, because it's not easy to use, but we're going to do that for 2 non-standard types of problems. Okay, so have a good day. Let me X out of here.